All right. So, section 10.6, that's to deal with the reaction quotient. Okay. Now, how do you know whether you've reached equilibrium in a reaction? All right. So you have these huge reaction vessels, like in a factory conditions, and you don't know if equilibrium has been reached. So you want to check how close you are to reaching that equilibrium, and then you will use this expression called as reaction quotient. It is exactly the same as the equilibrium constant expression, except it's not at equilibrium. It's done at a time which is not at equilibrium. It could either go beyond, it would have gone past the equilibrium time, or it could have been time before equilibrium. So with the HI experiment, for example, if you decided to test the reaction at 8 hours, you would have found that you have exceeded the equilibrium time. All right, so you've gone beyond the equilibrium time. Or if you tested it after an hour, you would have found that you have not quite reached equilibrium because you need another couple more hours to get to equilibrium. All right, so that's when reaction quotient becomes an effective tool for that sort of conditions where you want to check whether you've reached equilibrium. So the reaction quotient has the exact form as the equilibrium constant expression, but the concentration values are not those that are at equilibrium. All right, it could be at a time where it has not reached equilibrium, or it could be at a time that has passed the equilibrium. All right. Consider the following reaction where methane is made from carbon monoxide and hydrogen at 1200 K. All right. So you're making methane, CO, carbon monoxide, and hydrogen combining to make methane and steam. All right. Okay. So here you would you've been given the Kc for this particular reaction at 1200 K. It's 3.92. So you will write a QC, reaction quotient expression, just like you would a Kc expression. So it's product of products raised to their coefficient, which in this case is all 1, divided by the product of the reactants raised to their coefficient. All right. So CH4 times H2O divided by CO times H2 cubed. Okay. Now here notice the subscript here is this lowercase I, where I is the concentration of the reactants and products at a particular instance of time. All right, so it's not quite at equilibrium. Let's say that instance of time is 4 hours after that reaction started. So you want to be sure that you have reached equilibrium at the 4-hour mark. Okay, so you're going to be checking what those concentrations are at the 4-hour mark. You know the equilibrium constant, it has been previously tabulated that at 1200 K it should be 3.92. Okay, all right. Then what you do is you take all the concentrations of reactants and products, measure them, and then plug them into the QC expression. All right. So the CH4 and the H2O concentrations were both 0.001 each. The CO and the H2 concentrations were 0.02. All right. So plug it into the expression and you found that the QC value is 6.25. That means it's greater than the Kc. All right. So that means that you've gone beyond Kc. Okay. So you would have to go back the reverse direction so as to get back to 3.92. Okay. So the reactants need the reverse direction needs to happen to get back to equilibrium. Okay. So the reaction must proceed to the left towards the reactant side, all right, generating more of the reactants in order for QC to match up to Kc. Okay. So for a general reaction, if you have reactants A and B forming products C and D, you write the QC expression at the given instant. If QC is greater than Kc, the reaction will go left. If QC is less than Kc, then equilibrium hasn't reached. It will have to go right towards product. If QC is exactly equal to Kc, that means you are at equilibrium. Okay. So in a reaction vessel, these are the numbers you're given, all right? This is nitrogen and hydrogen forming ammonia. So you have 0.02 of the nitrogen, 0.06 of the hydrogen, and 0.01 of the ammonia, okay? Kc value is 0.5. The temperature at which this Kc value is listed is 400 degrees centigrade. Can you predict if more ammonia will form or some of it will break down back to reactants in order to reach equilibrium? All right, so you plugged in all the numbers, 0.01 squared, because that's the coefficient is 2 for ammonia, 0.02 for the nitrogen, and 0.06 cubed because there's 3 hydrogens. All right, so you got this value 23.1. Now this is way greater than 0.5. All right, so QC is greater than Kc, so the reaction has to go left, and some of that ammonia will have to break down to get to equilibrium. So here in this reaction vessel, you have 0.0015 of the CO2, 0.01 of carbon monoxide. This is a heterogeneous equilibrium, all right? So Kc is CO squared divided by CO2, okay? So 0.01 squared divided by 0.0015, okay? That's Qc. That's 0.067. So Qc is less than Kc, so the reaction has to go forward. More of the CO will form. And in this section, the last section, we're talking about equilibrium in aqueous solutions. So there are many ionic compounds that dissolve in water very little, all right? So they are generally insoluble in water, all right? But a small amount of it does dissolve in water. And so there is an equilibrium then that is established between the stuff that is not soluble and the ions that are soluble, all right? Like here, all right? So you have calcium oxalate. It's dissolving into the water. The solid stuff is dissolving into the water. A little bit of it is splitting up. So 2 halves, the calcium and the oxalate are half. But most of it is remaining insoluble. So you'll write the K expression for this. This is called as Sp here. Instead of Kc, it's Ksp. Sp stands for solubility product constant, right? This is Ksp is only used for aqueous solutions, okay? So Ksp is equal to the concentration of the calcium and the concentration of the oxalate ion, all right? Remember, solids and liquids are not included in the K expression, all right? But aqueous solutions are subject to changes in concentration, much like gases, okay? So Ksp is the equilibrium constant for a slightly soluble or nearly insoluble ionic compound, okay? So it says, write the Ksp expression of the following slightly soluble ionic compounds. AgCl, you know, is insoluble according to the solubility rules. It's only slightly soluble, so Ksp is going to be Ag plus times Cl minus. Ksp here, if you split it up, there's one Fe, 3 plus, 3 of those OH minuses. So Ksp is equal to Fe3 plus times OH times 3OH, right? So you have 3OH cubed. Okay, now here you have oops, going back. Yeah, so KSP is equal to Ag plus times Cl minus. Here it's going to be Fe3 plus times OH minus, and it'll be cubed. Okay, here it's going to be Pb2 plus and I minus squared, and here it's going to be Ba2 plus and SO4 2 minus, and then Pb 2 plus cubed and AS4 3 minus squared. All right, so just a minute. This is what it's going to look like. All right, so KSP here is just split them into two, Ag plus and the Cl minus, split them into two halves, the Fe3 plus, because it's a 3 on the Fe, each OH is negative, and then that's cubed, and then this is going to be Pb2 plus and then I minus squared, and then Ba2 plus and SO4 2 negative. And then there's a 2 plus on the Pb, but there's 3 of them, so cubed. And then there's a 3 minus on the AS4, and then 2 of them, so squared, right? A little bit complicated, but if you think about it logically, you will end up with these expressions. All right, so this is how the KSP expression is written for these slightly soluble ionic compounds. Okay, now you're asked to calculate the KSP once you're given the concentrations. Okay, so write down the KSP expression, that's Ca2 plus C2O4 2 negative, and then plug in the numbers. So if you have one of this, you're going to get one of this and one of that. If you have 0.00048 of this, you're going to get 0.0048 of this and 0.00048 of that. So 0.0048 squared. So the KSP is 2.3 times 10 power 9. Similarly here with PbI2, when you split it up, Pb2 plus and 2I minus. Okay, so KSP is Pb2 plus I minus squared. All right, so it's going to be if you have one of this, you get one of this, but then 2 of that. All right, okay, so 0.0012 of this, 2 times 0.0012 of this squared, because that's the KSP expression. Okay, so you get 6.9 times 10 power negative 9 for the KSP for PbI2. What if you're given the KSP and then asked to find out the solubilities? Okay, so you can take the aluminum and split it into two halves. All right, if you call this X, then that's 3X. Okay, so aluminum is X, the hydroxide, 3 of them, so that's 3X. And remember, in the Kc expression, aluminum is just 1, but this has to be cubed. All right, so it's 3X cubed. So that's 27X cubed times X, so 27X4. Similarly, if you do CaF2, Ca is X, that's F is 2X, and then you square it, so 4X squared times X, 4X cubed. This is simple, it's X and X, so that's X squared. CuOH2 on the other hand, Cu is X, and then the OH minus is 2X squared, so 4X cubed. And then the next is just taking the solubility, dividing it by that coefficient raised to the square root. Okay.